Okay, so the lecture is really about a little bit like a story sharing. So it's mainly about when I was doing my postdoc at York. It was back in year 2012 to 2015. So I did a little bit of research work about safety critical system. So that's something I would like to share with you. Okay, sorry, you may just adjust the slides. Sorry, it's not perfect. Yeah. Okay, now it's good. And now go away. All right. Okay, so I'm gonna give you some background about what this project is about. I believe that's related to your discipline, software engineering. Okay, I believe most of you are doing this. Okay. So now let's just start with that. So I work for McMaster University, also more like a joint supervision by Jonathan was one of my PN supervisors. And that's about McMaster Center for Software Certification. So there was a project they did. It was between year 2008 to 2016. It was supported by the Ontario government. Basically, that was about certification of safety critical software intensive systems. They got many domains over there for the projects. My part is about the nuclear domain. So I want to give you a little bit story about how things you learn in this course can actually be applied. Specifically, function tables and PVS. That's something you have been learning, right? Just to see what's the practical value for that, okay? I will try to restrict the background part to be very limited. You can definitely read the slide. I don't need to tell you every detail. But I do want to show the more technical part that's interesting. So the objective for the project is really to think about when you are given a piece of software, how can you be sure as a professional engineer it is fit for use and safe and reliable? So what kind of evidence you can provide? Okay. Okay, so we're going to develop methods, tools, and the tools I'm going to show you will be function tables and PVS. Okay, and also how you can certify certain things that's really important for your developments. Okay, for methods, and so these are all the other domains. Okay, that's involved in the project. But for mine, it's about nuclear. Okay, so have you heard about OPG? Maybe so Ontario Power Generation. So that's basically the Darlington nuclear reactor. They got 2 shutdown systems being refurbished. I was kind of part of the process for me and supervisors for their projects. And then the main contribution I'm going to present to you will be verification of function blocks defined in the standard components. Have you heard about function blocks before? Any one of you? Okay, it's basically one language, like a programming language, for you to define the system. Okay, I'll give you more example. We're going to talk about 2 case studies today altogether. Okay, my collaborators, okay, so these are people from McMaster University, and you can see Jonathan's name there. He was my supervisor at that time. And by the way, you can see PEng, professional engineers, because for safety critical projects, you need professional engineers to stamp on to give you, to make it certified. Okay, also some other researchers from Singapore. Okay. Anyway, so let's talk about how you can develop safety critical system. So one thing that's interesting is there are many industrial standards, like documents, to actually tell you if you want to develop, let's say, nuclear system, what's kind of the acceptance criteria they need. Okay, I'm going to show you some example. Okay, so one example will be in the aviation domain. They got this document called this name. Okay, I will show you one example for the nuclear domain. It's IEEE 7432. Okay, I believe I have it over here. I'm not sure how to get rid of the right panel over here, so bear with me. Okay, so basically that's the standard over here. It simply is the standard criteria for digital computers in safety systems of nuclear power generating station. Okay, that's actually a standard of several hundred pages. Basically, any engineer who wants to develop the system, they should consult with these particular documents. Upon completion, they should somehow argue how I have followed this standard to actually make it happen. Okay, and usually these cost a lot to actually purchase. Okay, so I'll just show you a little bit, okay, about the table of contents very quickly. Okay, what they put over there is nothing technical. It's basically just about what kind of criteria you should really satisfy. Let's look at the table of contents very quickly to get an idea. Okay. Let me just get there a few pages away. Okay, for example, you can see over here, they talk about the scope and also definition abbreviations. And this one is safety system criteria. Okay, basically they simply listed all the criteria you're supposed to satisfy upon completion. For example, you might have read about single failure criteria, which means you should have more than 1 point for your system. Otherwise, if that single point failed, the system can still run. Well, things like that. Also about reliability and etc. Okay? If you're the safety engineer for the nuclear domain, that's the document you should consult with. Okay? So that's my case. I consulted with that document. Okay? I just want to show you there's such a document. Okay, give you a little bit of summary. So for that kind of a standard, they gave you 2 important criteria that's relevant to my projects. One is about the system requirements should be precise and complete. Okay? And what you learn this course is very relevant. You learn about function tables. You know that function tables should have 2 healthiness conditions. You know which 2? Completeness, disjointness, right? That's something you have learned about. Okay? So the requirements are really important. We'll see examples at the end. And also, if you have developed your implementation in any programming language, for example, function block is one programming language, how can you argue that your implementation really conform to the requirements? That's another concern. So one is about requirements, the other one is about implementation. How can we satisfy that? Okay? That's really important research question we have. Okay? But now, how do we accomplish that? And why is this relevant? Okay? So now, I want to mention a little bit about the context. I believe all of you are in software engineering, right? Not all of you, many of you. Okay, at least in the engineering. Okay. For those of you who graduated, you want to go to the industry, you might consider being licensed as a professional engineer. Okay, that's a PEng that you saw besides the title of my past supervisor. If you became a professional engineer, let's say in Ontario, we got different associations across Canada, in Saskatchewan, in Alberta, in British Columbia, and also in Ontario, every province. Let's say in Ontario, they have something called a code of ethics, meaning that once you become licensed, you have to somehow comply with certain rules for conduct. Okay, let me just briefly mention to you why this will be important. Okay? Of course, you got to be responsible for the society, to your employers, your clients, your colleagues, and also yourself. Okay? So now, let's see. I'll go over very quickly. Okay? Fairness and loyalty, fidelity. Also, you want to have high ideals, which means you should not have any conflict of interest. Okay? And also, you should have good knowledge, meaning that if you know function table should be the way to go, you shouldn't really try something that's easier but less effective, something like that. Okay? And also, you want to remain competent. Okay? And then, if you fail any one of these, you know what the consequence is? Well, actually, you know, in some way, code of ethics tells that if you, for you as a professional engineer, if you want to practice your profession, you have to follow them. Okay, I would say, if you're lucky, then the consequence may not be so dire. Okay. Anyway, so possible consequence could be, well, you might just get your license suspended or terminated, which means you cannot really seal on the paper to say this is certified by me as a professional engineer. If you're unlucky, you might go to the court, because it costs your client to lose some money, okay, or even cost people to lose life. Okay, so that's kind of the context we want to have. So what you're learning in this course here is to see how you can have precise requirements in order to disambiguate or to remove all the inconsistency. That's really important step. Okay, to have some well-developed products. Okay, if you're interested later becoming a professional engineer, I believe maybe many of you really think about it, you can go to the link for Ontario. Okay. All right. So now let's talk about formal methods very quickly. So why is formal methods so important? Even in the industry, they advocated the formal methods. They believe it's about mathematical analysis that you can do, you can perform, and it can ensure correctness and robustness. What's the difference between these two? Correctness versus robustness. Anyone? Yes. Yes, exactly, yes. Yes, correctness simply means given some certain requirements for your software, you can conform to it. Robustness means you can handle any exceptional scenarios. Exactly right. Okay, good. Anyway, so formal methods can definitely help you deal with that. So far, you have used called a TLA. So that's a model checker. Basically, what it does is to systematically explore the state space of your system, right? That's one way to certify your products, model checking. However, you suffer from a state explosion problem. On the other hand, what you're doing now, PVS, is actually trying to do theorem proving using deduction. That's just another way to do things. But for you as a professional engineer, you should know when to use what and have a proper combination of these. Okay, that's kind of the knowledge you should have. Okay, but today we'll focus on function tables, especially how you do that in PVS. Okay, so formal method would be very nice to really have unambiguously describing software system requirements. And now, the second part is important, okay? You don't necessarily have to prove something when you use formal methods. Even if you just have the formal documents written down, it's a very nice, solid reference for discussion between your colleagues. So one of the case study I have at the end for you, I do have some examples to show you. Even have a function table itself, you don't have to prove anything. Even that would be valuable for communication, okay? Kevin, do me a favor. When we are about 30 minutes before the class ends, can you let me know? Good, thank you. I want to have at least 30 minutes to discuss a case study. Thank you. So now, and also you can provide some verification evidence. Okay, so now we talk about healthy condition and also satisfying safety property. Okay, that we'll talk about it, okay? Okay, so far just background. I just want to go over very quickly some diagrams with you and then have some discussion, okay? So basically, you can just go over the points over here, but I'll just talk about it over the iPad. Let me just move my slides over here so it's easier. Okay, let's have a look at this. And then let's distinguish between two terms. One is about building the products right and also building the right products. It sounds similar, but do you see the difference here? The two sentences? Yeah? Aha, sure. So I believe me Johnson talked about it already. Okay? So which one is validation? Is the first question about validation or the second question about the validation? Yeah, exactly. You want to make sure if the first one, make sure given the requirements, are you actually faithfully building the product according to the requirements? Number two is about is the requirement in the first place actually correct? Okay, good. Okay, so this is what you typically have to deal with. You have informal requirements over here. Okay, might just be in natural language, and then you're trying to develop some implementation over here. So this can be C code, can be Java, or can be IFO, right? You learned about IFO before. Or it can be, for example, function block. Okay, this function block is something we'll talk about today. Okay, so now if I want to know whether my implementation satisfies the informal requirements, it's not directly applicable because they simply belong to different domains, right? One is in programming language, the other one just natural language. So what we typically do is to translate them into the same language. So I will say translate and translate over here, right? For example, the informal requirements might be translated into PVS, okay? It's a function table for requirements. And also the implementation can also be translated into the same language, PVS. And then you try to see whether this implies this as a formal proof. That's what you do, okay? Let's say we follow this particular process over here. And one more thing. And it's very often that, let's say you're using Java, okay? You relies on Java API, right? For example, you might be using hash table, array list, or whatever Java library that might be available to you, okay? So now, my question for you is a very common issue here. Consider this guy here and this guy here. Potentially, what issues can we have? There are two issues over here. Let's say I did some very nice translation from my informal requirements from English to PVS. Let's say I do that first. Number two, I also try to do some translation from my implementation, which uses some library components into PVS. Let's say these two translations were done correctly, let's say. So these two are not a problem, let's say. Okay, and then also try to do some proof. But what's lacking here? Anyone? Yeah, sure. Because how do I know the Java API, for example, I'm using has been certified? Maybe it's developed by some wacky programmer, right? So this part has to be certified. Okay, that's question number one. Is it certified? That's one for sure. Another one? How about this guy here? When you said, I'm simply just going to translate my informal requirements into system properties, but how do I know if this particular piece of requirements is itself valid? Okay? That is, am I building the right products? So what's missing is this part over here has been validated. So these are the two issues over here. So this is a very general picture about if you got certain things you want to certify, you want to make sure the thing you're trying to certify against has been validated. And any helper library you're using in your programming domain has also been certified. So these are the two things. Okay? I'm going to show you both, okay, quickly, later. Okay, that's about it. So I'm just going to move on. Okay, everything has been said, so I don't have to bother you with that. Okay, so now we're going to see basically this. We're going to use function tables to document the requirements. Okay, we're going to see some example from nuclear domain. And Jonathan will talk a little bit more when he comes back. And then we're going to see, well, I wouldn't really go into too much about PVS detail. I'll keep it a little bit abstract level. And also how I can formulate, let's say, some programming library, like a Java API. Okay, and then how we can verify. Okay, okay, cyber-physical system. Okay. Basically, whenever people talk about cyber-physical system, that means you have some interaction between the natural environments and also the controller, right? So let me show you one diagram. So we got, are you familiar with feedback loops, sensors, and actuators? Are you familiar with it? Okay, let's just mention that quickly, just make sure. Maybe back in your 1021, you did lots of sensors and actuators, right? If you took it earlier. Okay, that's a very general schematic form. Okay, so now, basically, any cyber-physical system, you're dealing with some natural plant. It can be a nuclear reactor, for example, right? And then somehow you have a controller of the shutdown system. You have to monitor the temperature for the nuclear reactor, for example. So you got a number of sensors and also got a number of actuators. So basically, the feedback loop goes like this. You're just going to iteratively keep monitoring the plant, like a loop, okay? And then the sensor will tell you, for example, as soon as the temperature goes above certain range, you're going to use the actuator to trip and shut down the system, for example, right? So that's kind of the separation of concern. You got a plant, you got a controller, okay? And what I'm going to talk about is how we can certify this component specifically, the controller, not a plant. Okay? Just to get it clear. Okay, that's about the some terminology here, and then we'll go back here. Okay, the joint dynamics is really important, but we're going to focus on the controller, just to let you know. Okay, so this is more relevant to what I did. So there had been two shutdown system for the Darlington nuclear reactor. Okay, and then if you look at that, I'll just click on the link to see if I can go there. If I say aloud, what's going to happen? Okay, that's the picture for the nuclear reactor over here. And there are two shutdown systems for that. Okay, basically they keep monitoring all the critical variables for the nuclear reactor and then shut it down when it's necessary. Okay, so now I just want to show you the link. Okay, you want to make sure it trips if the reactor trips the reactor if you observe bad behavior. Okay, and there are, to really reduce the complexity, they actually got two completely independent shutdown systems so they can certify the isolation. You don't have to worry about the nuclear reactor itself. Okay, it's separate. Okay, so now function table. How is that relevant? Okay, so now just a little bit of history. So the original shutdown system was done in the late 1980s, maybe even before you were born, I guess. Okay? So now, the regulatory approval, for that to be approved, they kind of challenge the engineers the following question. How can you be sure that your system, the shutdown system, is going to perform correctly and reliably? And also, how can you remain correct and reliable when you try to maintain or have any future extension? At that time, their implementation was done, I believe, in Fortran. It's like a very old language. I haven't used that myself, but maybe some of you have seen that. Okay? And now, there's a prominent researcher called David Parnas. He actually argued that, okay, what we can do is we can try to create requirements and design documents. I'm pretty sure you're familiar with this term. That's what you have to do for this course. Okay? In the requirements and design documents, you have to somehow document the input-output behavior of your system using function tables with no reference to the code. Okay? That's kind of the practice they did decades ago. And then after that, you can do some verification, and then you can try to argue that your function table can imply the safety property. Okay? Okay, if you're interested, there's a paper there. I don't need to bother you with that. Okay? Function tables. Okay? I didn't know that if you how in-depth you have learned. Are you okay with the function table in general? Okay, can I assume you're okay? Okay. You got completeness, you got disjointness. Okay, anybody just tell me so that I'm convinced. What's the difference between completeness and disjointness? Ben.
Completeness is that you covered all the possible takeaways.
Yes.
And then disjoint is that all of the lines effectively correspond to different conditions, different inputs.
No, not necessarily. Not necessarily. Okay. That's good. That's good. You know, just good to check. So let me just say what Ben was saying is a misconception. That's fine. Okay. What Ben just said, what he said about completeness was completely right. Okay. So when you say, for example, C1 together with C1 or C2 altogether up to Cn should be equivalent to true. You cover all the cases. What you said was value 1 cannot be equal to value 2. You say map to different values, right? I believe that's what you said.
I'm saying that every input's taken into consideration, and there's no duplicate line.
Oh, you mean duplicate line? You mean for the output or the input? But what do you mean input condition doesn't duplicate? Maybe I misunderstood you.
Let's say, for example, you have like a binary truth table, right? You have like 1, 1, and then later you have 1, 1 again. You can't have 1, 1 mapped to 0 and then 1.
You always get the same row, you're saying?
You're always going to get the same.
Sure, but doesn't really cover disjointness. Mm-hmm. Kevin?
Condition should always yield the same result each time.
Well, the same condition can always yield the same result. Sure. Result. X larger than or equal to 0. X less than or equal to 0. I get value 1, value 2. What if I have over here x equals 3? I always get the same result, would I not? Agree? X equal to 3 will always satisfy the first row. I'll give V1 always. Does that mean the table itself is healthy?
No,
for all values. Mm-hmm. So but how can you formulate it, disjointness? Somehow, how do you know that this one and this one is actually not disjoint? What's the proof obligation here? That's my concern. For all values, I agree. Yes. Connor? Yes. Correct. That's correct. Yeah, basically. You're basically saying that for any of the two rows, the condition for over here, it is not the case that C1.1 and C1.2 can be true at the same time. Right? You got to do a pairwise assertion. That's disjointness. But you don't have to do this manual assertion yourself. PVS will generate the proof obligation for you. That's the convenience for using some tool over here. Okay? Good. Anyway, I assume you're okay with function table, so we can go directly to example. Okay, that's good. Okay, so now the completeness, disjointness, you're okay. So now what I will do is, let's do some example over here. Okay, this is one of the units in the shutdown system. It's called a neutron overpower units. Okay, just NOP. Okay, standing for NOP. Let's go over informally what it is supposed to do, and then tell me if you can imagine how the function table would look like. Okay. We have an NOP controller, conceptually, NOP controller. And then it has an output called C underscore standing for controller. Okay, NOP parameter trip, whether it should trip or not. And then it depends on 18 instances of the sensor trip. So that's why you can see NOP sensor trip of indices 0 until 17. So I got 18 instances. Okay, and then each sensor I, so let's say for sensor number 0, they depend on two things. Okay, one is about the NOP calibrated signal. Okay, that's signal number 1. Okay, it's index 0. And also there's certain set point. Set point simply means if the signal monitor value is strictly above certain level, you have to trip, basically, for this particular sensor. Okay? And now, how do we actually somehow formulate this in function tables? Okay? How many tables do we need? I heard 17, or 18 maybe, because you got 18 instances. But are you sure we need that many? Why can we not generalize it? For example, maybe a single table should be enough for all the possible sensors, right? Maybe one table for sensors, the other one for controller, possibly. Okay, let's have a look. Okay, I'll show you the some part of it, and then we can let you do a little bit exercise. Okay, let me just switch. All right, sorry, that's not the one. That's the one we just look at. This guy here. I kind of black out one part of it. Okay, let's have a look at this table here. Okay, this table here. Basically, you can see it's a function table over here. It should be quite. Let me just help you read it a little bit. Okay, here. You can see calibrated signal over here, calibrated signal over here, and calibrated signal over here. Okay, it's indexed by I. I can be from 0 until 17, so you don't need 18 tables. One table will be enough. Okay, they behave in a similar way. So now, can we argue that, first of all, this table is complete and disjoint? Just this table alone. Can we? Okay, let me help you a little bit over here. You can see kind of the inequality we set up. Over here, let's say, let me put red. You can see this is larger than or equal to. So this is strictly less than. And then less than or equal to, and then less than. So that will make sure it's disjoint. Let's visualize that quickly. Okay? So now basically you got something like this. So you got over here called FNOP set points. Okay, I'm talking about this guy here. Okay? You got another quantity over here called FNOP set point minus some constant. So K stands for constant. Okay? So now you got another constant, another quantity over here is the FNOP set points minus the constant of NOP HYS. HY stands for hysteresis. Jonathan will give you a little more complicated example when he comes back. I'll just do some very simple one. Okay, we got these two quantities. Okay, and we are saying the following. For the first one, we are saying that if your calibrated signal, let me use different color, is larger than or equal to, right? You do something, okay? And then the second one, you're saying that if it is strictly larger than that, strictly less than that, and also strictly larger than the second quantity, right? You're somehow between here. Okay, you do something else. And then finally, you can see it's less than or equal to, right? Less than or equal to. Okay, so the inequality has been set up very carefully so they have no overlap in terms of input condition. Okay, you okay with this? Okay, so now the only thing you have to pay attention to is the result can be either it's going to trip, which means it's going to warn the controller, or it's not going to trip. And now it simply says it's going to remain to be the same as before. Okay, so either of the three outcomes. So now I have a little exercise for you. Given that this is how we set up the table, okay? And by the way, Jonathan will actually talk about, I don't want to take your time for this. He's going to talk about, when he comes back, why do we have 3 different regions for this particular signal? Okay, he will talk about it, hysteresis. Okay, but for now, I just want to show you how you can argue about completeness and disjointness. how can we fit out this condition over here? Remember, this table here can be instantiated for I between 0 and 17, okay? And now the idea is the table for the controller is going to tell you the controller can either trip or not trip, depending on the following condition. I'll say that informally. If any of the sensors says you should trip, then you trip. If all the sensors say you should not trip, then you don't trip. So now, can you give me some suggestion for these two conditions over here? What kind of mathematics should we use? What kind of quantifier? Or I already told you the answer. What kind of expression should you write? Yes. For all, where? The first one or second one? You mean for all? You mean saying if for all NOP sensor they say trip, then I trip? But would that be consistent with the informal requirements? I said that the informal requirement should be the controller trip if any of the sensors actually give you a warning. Yeah, the second one. Okay, good. Okay, just be careful. Okay, so now let me just tell you the answer quickly. Okay, it's a very simple one to write. Okay, basically what you will see is exactly what I said. So now if you look at that, if there exist any of the sensor that says trip, then you trip. On the other hand, if all the sensors tell you that you should not trip, you don't trip. Guys, make sense? That's a very typical function table. You can see that's actually not too much more difficult than the one you have been using, right? But that's being used practically. Okay? That's part of the requirements document for the shutdown system, part of it. Okay. Any questions about this? Okay, that's your first function table. All right. We're going to see more. Okay, so after this, I'm going to look at a little bit more on the slides. Okay, that's exactly what you see eventually. Okay, PBS, you all know about PBS. You can write specification, you can write proofs, and they got direct support for the tables, right? They can also generate the type correctness conditions, right? For disjointness, completeness, okay? Okay, we're gonna see now PLCs. So the project I was involved, somehow they want to re-implement the shutdown system. Rather than using Fortran, they wanted to use something called PLC. Have you heard about PLC before? Programmable logic controllers. I'll show you some visuals, okay, just you can get some idea. And then we'll get to the programming part. Okay, PLC. Okay, I simply got this diagram from some book, so I want to make some disclaimer for copyright. That's how the PLC look like. Basically, you can imagine that that's kind of the controller over here. They also got some input port and also output port over here, okay? And they have been used for automation and also product line. You know, that's kind of the usages, okay, PLC. So now, if you look at the left-hand side, that's how people program controller system before. It's called a relay-based. Basically, you have to program according to the combination of the cable in the port, right? You can see which combination to go. On the other hand, if you simply got a PLC-based control panel, you just have to just connect to your input-output, and that's it. You don't have to worry about the combinations, okay? More precisely, if you look at that over here, okay, let me see this, okay? So this is the PLC over here. So now for the input, you have, so input, you got push button, you got limit switch, also you got sensor. You can get as many input as you like. Okay, just connect them to the input port. And also you got contactor, you got light, you got different stuff over here. Okay, you got different input, you got different output. Okay, also you got a controller over here, and then you can load certain program into the controller. Okay, there are different languages you can write for the controller. So function block diagram is one. Also you can write something similar to Pascal. You know, it's a block syntax language. Okay, different languages. Okay, so now this is how the PLC work at runtime. Again, it's a cyclic executive. Basically, you're just going to monitor all the inputs that come in, and also try to execute a program using the controller logic, and then try to update the output using actuators. Okay, that's kind of the big picture, okay, for PLC. Let's see a little bit more diagrams. Okay, so that's the input module over here, and that's the output, and also you got the memory with the program, and then you can also program on your device. Okay, and very valuably, they also have debugger for the program, like what you did in Visual Studio or Java, Eclipse, right? You got debugger. So if you program in PLC, it's actually much better than using relay-based system. Okay, much easier to build large system. Okay, so now I want to talk about some case study. Okay, how did I use PVS, and also function tables, to certify components? So basically, what I'm talking about is this particular part. Let me just mention that quickly. What I said before, this diagram over here, when our implementation is actually using some library components, you want to make sure that library component is somehow certified. You may have to prove every method that you might want to use in that particular library. Okay, let's see how we can do that. Okay, and I'm going to show you some example. Okay, so the library I talk about is so-called IEC. Is another standard. Okay, just an industrial standard 61131 for PLCs. Okay, at the end of the standard, they got an Annex F. Basically, they simply got a library of function blocks. You can think about function block is one way to program the PLC, just like a block diagram. Okay, so now I'm going to show you quickly how you can use a formal approach to certifying the library. Okay, let's see. And then we consider two example issues. Okay, so we got time. Okay. Okay, we got function blocks. Okay, and then we're going to see examples. Function blocks, and then the standard. I tell you the conclusion right away. The standard was published in 1993. It's been used for more than 20 years. After me and my colleagues, we try to formulate every function block in the library. And then we try to see if there's anything missing, anything ambiguous, or anything inconsistent. Okay? And then over there, they try to present to you different languages. Okay? The two I focus on are function block diagram, structured text. Structured text is like a programming language, like a Pascal or IFO. Okay, also they got basic function block, and they also got composite function block. So Jonathan will talk about hysteresis being basic, and also limits are long called composite. He will talk about it when he comes back. Okay. So now, every PLC engineer, if they want to develop their function block-based system, they have to somehow show compliance with this library over here. Okay, I'm going to show you quickly the library. Quickly, it's documents again. Okay, it's IEC. Okay, I'll make it a little bit bigger for you. Okay, sorry. I'll read it to you. It's called Programmable Logic Controllers, and then it's part 3, Programming Languages. Okay, so now if we go to the Annex F, okay, let's see the table of content. They simply just introduce different languages, different notations. You can see over here, Annex F. They simply call it informative examples. Over there, in that particular section, they list different function blocks. Let me just go that section there to show you. Okay, so I can go to 169. Let's see some example over here. Okay, you can see that basically they start with over here 169. Okay, for example, over here, that's kind of the basic layout for the library. They present one block after another. So for example, this is one of them. And then the one that Jonathan will talk about next week will be something called hysteresis and limits alarm. For example, you can see one here. Oh, let's see here. You can see this guy here is called average. Let me make it bigger. So 35. Okay, good. Is it readable to you? Average? Okay. You can see this is the average block over here. They simply give you interface for the function block and say that it's going to take some input of type Boolean, real number, and integer, and it's going to return some real number as output, right? How exactly it works? Sometimes it may simply just give you some example implementation. However, they show no evidence of the implementation being correct. They also didn't show exactly how the average is supposed to work. Okay, that's a problem. Okay, so me and my colleague, we simply just went over block by block to see what issues we can find. Okay, we're going to show you 2 issues today. Okay. Okay, let's go back there. Okay, so now, can I? That's really, yeah. Good. Okay, we use function tables. We use now we examined 29 function blocks in the library. 29. Okay, it's the basic one. We found 10 issues. I would say they are not very small issues, as you will see. We even found inconsistency in the blocks, and then this standard has been used for more than 20 years. And if people simply copy and paste those blocks, then they are not really building a reliable system. That's a problem. Okay, we're going to see 2 examples. Okay, so what I will do is I'll go over the approach very quickly, and then I will talk about the 2 case studies, and then that'll be it. Okay, I don't want to take too much time. Okay. So now what I will do is I will go to this diagram over here. Let's talk about this diagram very quickly. Okay, that's the overall approach. If you're really interested in the approach, there's a journal paper we published. You can definitely refer to it for more details. Okay, just give you an idea overall. So this part over here is the standard that I just went over briefly. Okay, it's an IEC 61131 standard. Okay, all the description are in natural language, it's English. Okay. They simply use English to describe each block informally, and then they give you sometimes function block diagram implementation, sometimes some structured text. Okay, ST standing for structured text. It's just a programming notation like a Pascal or Java. Okay, sometimes they give you both. When they give you both, you have to make sure they're consistent with each other. But it turns out they are not necessarily the case. Okay, we'll see. As I said before, when you get something that's informal, you have to formulate them into some common language, in this case, just PVS. So we actually translate the informal requirements into function tables in PVS. And also we translate implementation into PVS, and we try to prove them. Okay, and let's see what happened. Okay, that's kind of the overall picture. And also we got things like consistency and also correctness. Okay, that's kind of the stuff we have to prove. I wouldn't bother you with the theory. Okay. So now what I want to do is to do 2 examples quickly. So these are all the issues we found. Well, just some of them. Okay, we found ambiguous behavior. We found missing assumptions, also wrong implementation. Okay, these are the issues we found. Let's do examples together. Okay, I think I got some printout for you, so you can look at that. We can discuss. I think we got about. Hopefully we got 20 minutes, and we can get it done. Okay. Okay, you want to pass this around, and then, okay, let me pass this side for you. Okay, hopefully that's enough. I only got 20 copies. Because Kevin told me that there should be no more than 15 people. You guys might impress me today. Maybe that was intentional, right? Okay, have a look at that. Look at the one with the, okay, oh, you know what? I'll show you the one you should look at first. The second one is more interesting. Let's look at the first one first. Look at this one. Have we got enough? I hope. Oh, just enough? Wow, that's good. Okay, 20. Good. All right, the first one. Basically, the first one here, let me give you a little bit intro over here. You can think about the left-hand side over here is a function block diagram for implementing stack of integers. Okay? The right-hand side somehow shows part of the implementation in structured text. Basically, what we are talking about is this situation here. For the same block called stack of integers. Let me just use a different color. So for stack of integer, for this particular block, we show both function block diagram on the left-hand side and also structured text on the right-hand side. Okay, got 2. So now, here's one important issue. These 2 implementations were suggested using different languages. They must be consistent with each other, right? Otherwise, when you choose one, you might miss the other. Okay? Now, you don't have to worry about too much about how the function block diagram works. That will take some time to explain, but I can give you a little bit hints. Have a look at the right-hand side, the else if condition over here. And that one should be readable, right? It's a programming text. We are saying that if it is not a case, there is an overflow, OF standing for overflow. If there's not an overflow for the stack, then we should really try to output the top of the stack, something like that. Now, if you look at the left-hand side, okay, notice that there's an overflow output signal from this block over here and goes all the way. Oh, no, I can actually explain that on the iPad. I forgot. Okay, let me say that again. This is to say if there's not an overflow, we're going to output. Okay, it's not overflow. And then look at that. The overflow signal goes from here, and it goes as an input to over here. There is some inconsistency over there. There is. So I say it again? Inverter for which one? The left or the right?
For the left.
Yeah, so exactly right. Yeah, okay. That's you would think that's obvious, right? But this error has been there for 20 years. Yeah, interesting. Yeah? Okay, you're exactly right. What happened was, you can look at that. This signal was passed directly into here, meaning that it says that if there is if there's an overflow, and then I'm going to do exactly what the structure test is going to do. So that's where we got the inconsistency. Okay? So you can see here we got a negation over here. But here we don't have negation, like an inverter. We don't. That's the inconsistency. So now we are facing a situation here. We got two implementations that are not consistent. We got two choices. Either we fix the function block diagram or we fix the structural text. Which one should we fix? We can also take out the not from the right-hand side. Does it make sense to take out the right-hand side? Yeah?
How do you know which one was the intended one?
Absolutely right. So let me just repeat what you said. How do you know which one is intended? Maybe the right-hand side is intended. Maybe the left-hand side is intended. But let's say this. Hypothetically, let's say we decided to take out the not. Let's say. If we did that, that simply means what we intended was as follows. If the stack has an overflow, we're going to let you pop it up. But would that be really what you intended? Possibly not, right? We just want to think a little bit more, think about the real sense. So that's why we thought maybe what's really intended is when there is not an overflow, then you can go ahead and pop it up. So that's why you should really add an inverter over here for the function block diagram. Okay? That's just one issue over there. Okay, guys, make sense? Okay, just one simple case. Okay, this one is interesting. Okay, we just found that you got two possible implementations for the stack of integers, but we found that they're not consistent. Let's see the second one. The second one requires some thinking. Yes, Connor. I tell you it's very interesting. When we were trying to write this paper here, we first presented in the conference there, and then we got invited for journal. The reviewer, when they saw this error over here, they said to us, did you realize in version number 3, which was published about 2 years ago, like 2013, they got rid of this function block library. If they're already gone, then there shouldn't be an issue. I would say, no. What if people are still using the old version? In that case, yeah, it's scary. The old version has been used for more than 20 years before the new version was out. Taking that out is not a solution, right?
Like they just removed this.
They simply remove completely Annex F. So now if you go to the latest version, version number 3, which was published 2013, you don't see this library anymore. But I doubt if all the people are still using the latest version. I doubt. They might be still consulting with this. Mm-hmm. Yeah. It's weird. Yeah. And actually, that's quite an obvious error, right? Yeah. Maybe when the programmer was trying to use this block, they realized right away and adapt it. But what if some people simply copy and paste? Scary. All right. Let's see the second one quickly. The second one requires a little bit thinking. Okay, let me guide you through it. Okay, you got to you can flip it. Let me just give you some initial requirements, informal. Okay, basically we are talking about a counter. Okay, a counter can either go up or down. So you can think about there are two units over there, up counter and down counter. Okay, so my color convention is red means output, green means input. Let's say there's an output counter value CV. The counter value might be set differently depending on the input conditions. Let's say this. The counter value might be incremented if the input condition CU is actually rising, which means it becomes true. Okay? It might be decremented if the input condition CD, CD means counter down, counter up, right? So green one. If CU is actually true, it's going to increment. If CD is true, it's going to decrement. And then you want to, and also the way you do the increment decrement should be subject to some PV max and PV min. Okay? Maybe only you only try to increment up to PV max and only try to increment down to PV min. And then initial value for CV can be set differently. It can either be loaded to a preset value PV, okay, some value. If the input condition LD, LD standing for load. If say load is true, then you should reload the initial value to be PV. Or it should be defaulted to 0 if the R standing for reset is true. Okay, you got many input and output conditions here. And then finally, we've got two Boolean outputs over here. One is called QU, okay? So Q usually stands for the output. So QU will just be the truthfulness of CV larger than PV. And also QD will be CV less than or equal to 0. Okay, that's all. That's informal requirements. And the only documentation you have from the library is this. I'll go back to the description so you can still refer to it. So this is more like the API for the block, right? You can see on the left-hand side, you got the various input condition over here. And also here, you got the 3 possible output, okay? On the right-hand side, I do encourage you to read it a little bit, okay? It's quite clear, okay? Basically, it's more like a block syntax code that tell you that this is the function block, the structural text implementation. Okay, don't forget one thing. Okay, imagine over time you're just going. Let's say this is a block. Okay, function block counter. You're going to invoke this for many times, right? So once you invoke that, you're gonna go back and invoke it again, right? Because whatever output it is currently is gonna be the input for the next run. Okay, it's gonna be invoked continuously. Okay, I'll give you a few minutes. Okay, if you want to get yourself familiar with it. Especially, I want you to pay attention. I'll give you a little bit of hints. Otherwise, it can be a little bit too challenging. Pay more attention for sure to this block. Think about this as everything you're given, nothing else. Do you think there's anything that's missing? Missing in the sense that without it, you might have some weird behavior for your function block. You got something? Okay, just one moment. Yeah. If you got something to say, please hold it. I'll just wait a bit for your colleagues. Okay, let's have a few minutes. Yeah, it's pretty similar to IFO, right, in some way. Pretty similar. The algorithm itself might be okay. Do you think there may be anything about the input or maybe some assumptions we should have made? If you think. Do you want to say your thoughts first?
My thoughts were that if CU and CD are both true, they're both set, then CV is kind of doesn't change really.
That's true.
But then CU and CD are both separate.
Yeah, actually you can see, yeah, you're right. Your observation is you will only go into this particular if block if they are not true simultaneously. What if you have CU and CD being true at the same time? That simply means for that particular run, you wouldn't change the value for CV. That's okay. Mm-hmm. Connor?
It's like assuming that only, I guess it's kind of, feels kind of ambiguous because you can go if R then CV is preset. But what if you had R and load, for example?
Yeah, somehow you go with some precedence. So you always check for R first.
Okay.
If R is already true, then you simply reset it, and that's it, and wait for the next round.
And is that captured in the function block by the order of it, or?
Oh no, the function block over there, that one's more like an interface. Just tells you what are the input, what are the outputs. It says nothing about the behavior, the left-hand side. Yeah. So for this particular block, for the counter, they didn't give us any function block diagram. They only gave us the API and also the structured text. Okay, just remind you, okay, so think about if this is a plant somehow, and this is our controller. And now the controller contains just this particular block, let's say. And then it's going to be cyclic executive, right? It's going to keep feeding input and keep generating output, goes continuously. That's kind of the thinking you want to have. Kevin?
I think it's making an assumption that PV min is a negative number rather than
It's making the assumption that PV min is negative?
yes.
Why would you think so?
Because
You mean it should make this assumption or it's making this assumption?
it's making this assumption.
How do you tell?
Because
From which line, if you can tell me? So what Kevin said was somehow it seems like they're making an incorrect assumption that PV min is simply negative. But how did you infer that?
well, because when they reset it, they set it to 0.
Mm-hmm.
And then when you count down, they stated that CV has to be greater than PV min. What happens if PV min is positive number? It will never count down ever.
Okay, so let's say if you set CV to be 0, let's say for the current round, and then come back next time. Let's say somehow if you actually satisfy this particular assumption over here, you're saying?
Yes. But for it to be satisfied, PV min has to be a positive number.
Yeah, that's for this particular scenario, but not necessarily just a particular run. Yeah. Okay, should I give you a little bit hints? Okay, how about a little bit hints? Okay, yeah. Okay, but you can kind of see the process we want to go through, right? When you look at the code, if you only look at that manually, it's kind of hard to think about. But if you try to turn this into PVS or some function table, you actually see there may be something missing. Okay, let me give you a little bit hints. At least you are familiar with what's going on over here. Okay, look at your code. Let me present the hints to you. Did they say the maximum must be strictly larger than the minimum? Did they say that? Did they document it somewhere? You would think that's the case, right? They said nothing about it in the program. Did they ever check? Yeah, they didn't say, for example, if it is not the case, PV max larger than PV min, throws an exception. They didn't say anything like that. So let's say, so that means that might be allowed. If that was allowed, what's going to happen? What would be the consequence? Let's say PV max is less than PV min. What will be the consequence of this? Are we going to get some very weird counter? Okay, let me help you just a little bit more. Okay, think about the enabling condition. What's the enabling condition for the counter? Well, if you look at that, basically, let me show you that. The enabling condition is such that, right? So these are the two. So that CV must be less than PV max, and CV must be larger than PV min, right? That's kind of implicit from the code. So now, let's say if we have this, what's this will turn out to be? I'll give you a more concrete example. What if I have PV min 10, PV max 1. And then the counter value will only be enabled if the counter value is less than the maximum, greater than the minimum. What would that be? Huh? They will never be enabled, so which means that's equivalent to false. So that means if you somehow set your PV max, PV min globally wrongly, let's say this, which they never constrain, by the way, that means your counter can never be used. Then what's the point? Yeah, guys, you see my point here? Okay, so somehow this assumption here was never mentioned in the standard, never mentioned. Okay.
It's like the same for CU and CD. You could also just say the same.
True, that can be true as well, but they're more like an input monitoring condition. PV max, PV min is more like a preset value that they kind of stay there forever. But CU and CD, they're more like a monitoring condition, so they might just change as environment changes. It's a little bit different, yeah. Okay, that's one. Okay, how about we see another one, okay, quickly. Okay, and then I'll show you a function table for resolution, and then we are done. Okay, let's do one more. So now, let's say this one also is interesting. What if, let's say the preset value, let's say load is actually true. That means we have to load the preset value to CV. However, the preset value is actually less than or equal to PV min. Meaning that now CV is now loaded with PV, which is less than or equal to PV min. What's going to happen here? In that case, do you think the counter will become disabled or enabled, or it doesn't matter in that case? According to the code. So the part you should really look at, okay, you can think about it a little bit more. I'll just tell you. Okay. So basically, you want to think about over here. It's more about, again, this condition over here. Okay. Okay. That's the part you can also look at. Sorry. Okay, you can look at that, but let me do a little bit of analysis for you. You can try to see. That's basically the kind of mathematical analysis you can do either by hand or using PVS. Okay, so now let's say we load the value of PV into CV, where the PV value is simply less than or equal to minimum, let's say, if we do that. So now, what will be the enabling condition for decrements? Okay? Enabling condition for decrements will simply be, if you look at the code, it's going to be CD and also CV larger than Vmin. If you do that and do some substitution, you're going to see that basically it's going to be PV, right? Because CV has been loaded with PV. So now, do a little bit derivation, you can see that here, if PV is less than or equal to PV min, but the enabling condition is larger than, they're completely opposite to each other. So that means it will just be false. That's another thing they should have made it clear. So that means it is possible so that you can set the PV to a value that you will never be able to decrement the value of the counter anymore. It's possible. But is that really what you intend or not? Maybe yes, maybe no, but I should make it clear so we can discuss. Okay, finally, so these are the two example issues I want to show you. Finally, I want to show you what can we do to make it very clear for communication. Function table. Let's look at the final function table here, just as a case study quickly, okay, and then we're done. So now, this is like a function table. Have you got anything this complicated so far? Maybe it's a nice case study. Maybe refer to it, okay. Now, we try to outline a table such that it's very easy to argue about completeness and disjointness. R or not R, okay? LD or not LD. And we got two Boolean variables over here, CU, CD. It's like a 0, 0, 0, 1, 1, 1, and 1, 0, right? All the four possibilities. And then over here, we also talk about the CV, the previous value is less than or larger than or equal to. Larger than or less than or equal to, right? You just got different condition laid out. So that's guaranteed to be complete and disjoint. And then you can just talk about what should be there. And then we also document the assumptions over here. Okay? So that's kind of the function table you can have to really help formulate the requirements. Okay? Anyway, any questions about this example here? Okay, so that'll be it. So just mainly just to share some story. I want just point to you some reference if you're interested. I intended not to give you too technical details, just to give you a motivation. So there's some valuable application by PVS and function tables in the industry. Okay, that's exactly what we said. If you're interested, feel free to go to the paper. We got many more function block issue over there. You can have a look. Okay, good. Thank you.